Hello everyone, myself Shweta Shah. We are here for the subject Computer Organization and Architecture. In this subject, we have started with Unit 1, that is Computer Data Representation, Register Transfer and Microoperation. And in this unit, we are going to see today the topic that is fixed point representation and floating point representation of binary numbers. Okay, in this topic, we are going to see how you can represent your binary numbers, whether they are positive or negative, or whether they are in fractional pattern. Okay, so first we start with the fixed point representation. If your number is a positive or negative in terms of binary, so you can check it by its sign bit, and that is rightmost bit, that is MSB bit. Okay, if this MSB bit is 0, that your number is a positive, and if it is 1, then your number is a negative. Okay, so for when your number is a positive, the sign bit you have represented by 0 and magnitude by its positive binary number, or you can say its quantity. Okay, but when your number is a negative, okay, then you have to represent sign bit by 1, but rest of the bit, or you can say its magnitude, you can represent by any of three methods, like sign magnitude representation, or sign 1's complement representation, or sign 2's complement representation. Okay, so if your number is a positive, then sign bit is 0 and rest of the bits are given. If negative, then sign bit is 1 and rest of the bits can be any of these three method, with any of these three method. Okay, so let me see with one example, it will more clear for you. If we have a number that is plus 14, so we can represent this number in terms of 8-bit representation as a 0 0 0 1 1 1 0. Okay, here 1 1 1 0 is 14's binary representation, and this 4 zeros are extra appended because we have represented this 14 number in terms of 8-bit representation. Okay, but what if your number is a minus 14? So if your number is a minus 14, then you have three representation for this, that is sign magnitude, sign 1's complement and sign 2's complement representation. For any of this representation, your sign bit will be 1. Okay, as our plus 14 has a sign bit 0, but for minus 14 your sign bit will be 1. But rest of 7 bit can be represented in terms of sign magnitude, or 1's complement or 2's complement. In sign magnitude, we are only using as we have used in a plus 14, we are only using same pattern for this. So sign bit is 1, rest of the 7 bit will be same as a plus 14. Okay, but this sign bit will say that your number is negative. Okay, for 1's complement method, you have to find out the 1's complement of the 7 bit, that is 0 0 0 1 1 1 0, and for its 1's complement it will be 1 1 1 0 0 0 1. Okay, and extra you have to append sign bit as a 1 if you are using 1's complement representation. And for 2's complement representation, you have to find out the 2's complement of this 7 bit, and that will be 1 1 1 0 0 1 0, and append sign bit as a 1. Okay, so by this way you can represent your sign number in fixed point representation. Okay, for positive number, sign bit is 0, for negative number sign bit is a 1, and rest of the bits can be in form of sign magnitude, or 1's complement or 2's complement of the actual number. Okay, so by this way you can represent your number. But what if you want to do the addition or subtraction or any kind of operation for this fixed point representation of number? So let me see the simple arithmetic addition operation. For example, if we have this numbers like plus 16 and plus 13, or minus 6 and plus 13. So for this numbers, you just require to represent these numbers into same method. Okay, so for plus, we positive number, we know that sign bit is 0 and rest of bits represent the magnitude. For a negative number, you can represent this into ones complement, two's complement, or as it is, or you can say in magnitude form. Okay, but here for simplicity we are going to use always two's complement form for the negative numbers. Okay, so here for plus 6 you have used its sign bit as a 0 and rest of the bits as a magnitude. For minus 6, here we have 1 as a representing sign as a negative, and rest of the bits are in two's complement of this positive 6. Okay, and 13 as it is a positive number, so sign bit is 0 and rest of the bits as a magnitude. Okay, and then whenever you are do addition of this number, 0 plus 1 that is 1, 1 plus 0 that is 1, and then 0 plus 1 that is 1 plus 1 that is 0, carry 1, and so on. Whenever you find out this addition terms, and if you see this sign bit is 0, that means your addition or result is a positive. Okay, let me see further examples in this. If your number is like plus 16 and minus 13 and minus 16 and minus 30. Okay, so for that your result will be negative. If you do addition of 6 and minus 13, your result will be minus 7, and for minus 6 and minus 13 your result will be minus 19. Okay, so for this case, whenever your result is a negative, and you have used two's complement method, your sign bit will be 1. And whenever your sign bit is 1, it shows that your number is your result is a negative. And to find out actual result, you have to take second time two's complement of this result. This quantity is true in terms of two's complement. Okay, but if you want to find out what is actually this quantity, if you consider this, it is not a by bit pattern for 7. You can say that this is 7, but it is the two's complement of 7. Okay, so whenever you see 1 as a sign bit in result, you have to take second time two's complement to find out the actual number. Okay, so this is for addition or subtraction operation, that what you require, that you require that your negative number must be represented into two's complement form. And if in each and every case, if your result is a negative, then your sign bit will be 1, and if your result is having sign bit as a 1, to find out actual quantity you have to take second time two's complement. Okay, so by this way you can do addition and subtraction operation for your two's complement or your fixed point representation of number. Okay, next we will see floating point representation. Okay, here in floating point representation, each and every number will have two parts, that is mantissa and exponent. Mantissa, or you can say fractional part. Okay, here this mantissa will represent the sign fixed point number, and exponent will represent the position of decimal point if we consider a decimal number system. Same thing will be applicable to binary number system. Okay, so let me see one example with decimal numbers. That is, a number is given as a plus, or you can say positive 6132.789. And if we want to represent this number in terms of fraction, or you can say fixed points, and in terms of exponent, then we will have 0 point, we will shift this decimal point over here. Okay, so that means we will find out some numbers in terms of 0 point something kind of. Okay, so we will have number like 0.6132.789. okay, but this is not an actual number. Our actual number is 6132.789. This is just a fractional part. To actually find out what is the number, you have to multiply this with 10 raised to 4. Then and only then it will be your actual number 6132.78. So here our exponent for our base 10 will be 4. Why? Because we have shifted 4 points, 4 times this decimal point. Okay, so our actual representation of the 6132.789 in terms of fractional and exponent will be 0.61378 and 10 raised to 4. So here 0.61327889 is our fractional part and 4 is our exponent part. Okay. So any number system, we can for any number we can represent this in terms of mantissa and exponent. Okay, and it will be represented as a m into r raised to e. Here e represents the exponent, r represents your base, and m represents your mantissa. Okay, so for any number system we can represent like this, and that is true for binary also. Okay, so for this conversion you will require to normalize the number. Okay, a floating point number is said to be normalized if and only if the most significant digit of mantissa is non-zero. Okay, for example, if we consider this number 350, it is normalized. Why? Because its most significant bit is non-zero. But this number 00035, it is not normalized because its most significant bit is 0. Okay, so first we will require to check this whether your number is in a terms of normalized or not. Okay, so for floating point representation we have some fixed format that is known as ANSI 32-bit floating point format. In this we will represent each and every numbers in format of this 32-bit. Okay, and in this 32-bit representation we have meaning for each and every byte. Let me see what is this 32 bits represents. Okay, as we know we will represent these numbers in terms of mantissa and exponent. Okay, so here this first byte will represents your exponent and the sign of mantissa, whether your number is positive or negative. Okay, so first byte is allotted for exponent and sign of the mantissa, and second, third and fourth byte represents your normalized mantissa. Okay, here mantissa is in second, third and fourth byte, but sign is given in a first byte. Okay, but you will have question that there is also possibility that your exponent is a negative. That is also a possible thing that your exponent is also a negative term. Okay, so you have to represent if your exponent is a negative, then in this 7-bit in terms of 2's complement. Okay, that means whenever your exponent is negative you will represent this exponent in terms of 7-bit 2's complement representation. Okay, and whenever your mantissa is negative or positive you have to represent this by s bit. If it is negative then 1, if it is positive then 0. Okay, and here you will require normalized mantissa. That means your rightmost bit, or you can say this m bit that is after this binary point must be 1. Okay, so let me see with one example, one or two example, it will make clear. So I have given this format second time, and let me consider if we have a number that is 13. Okay, the binary pattern for 13 will be 1 1 0 1. Okay, but it is not normalized. When it will be normalized when you have this binary point with after that binary point number is 1. Okay, so here we have binary point at this position after 1 1 0 1. After this one we have binary point. We have to shift, and this after this one we will have rest of the bits as 0, because there is no meaning of writing any number after binary point if it is 0. Okay, so next we will normalize this because it is not normalized form. To normalize this, what we require to have this 1 at rightmost position. Okay, so or you can say this binary point to at this position. So to shift this binary point we require to multiply this number by its power, basis power. How many times we have shifted this binary point? We have shifted this binary points 4 times. So we have to multiply this with 2 raised to 4 as our number remains as it is. Okay, So our representation for this 1101 in normalized term will be 0.1101 into 10 raised to, into 2 raised to 4. Okay, here our base is a 2, exponent is a 4, and mantissa is a 1101. Rest of the bits we have to represent this mantissa in this 4 byte, that is almost 24 bits. Okay, but we have only 4 bits, so we will use this 4 bit and rest of bits will be 0. Okay, so this is our mantissa part. After that mantissa we have binary point, and then there is a first byte. What this first byte represent? This represent your exponent. What is the value of exponent? That is 4. So we have to represent this 4 in 7-bit representation, and that will be 0000100. Okay, and this S bit represents your sign, and here as our number is a positive, that means our mantissa is positive, so we have to represent it with 0 to represent the positive number. Let me see another example, that is negative. For example, we have number like -17. Okay, so to represent this number we have bit pattern for 17 is a 10001, and if it is negative we have, for simplicity, we have put over here minus. So this is not a normalized number. To normalize this number we have to shift this binary point 5 times. So our normalized number will be 0.10001 into 10 raised to 5. So our exponent is a 5, mantissa is a 10001, and rest of the bits are 0. And your sign bit for this representation is minus, or you can say 1. Okay, so here your mantissa, then binary point, and then exponent. Exponent is a positive, so we have represented this in a 7-bit as a 0000101. And next, that sign bit, that is 1, because this number is a negative. Okay, there is also possibility that your exponent is a negative, and at that time you have to represent this 7 bits in terms of 2's complement of that actual positive number. Okay, so by this way you can represent your floating points number. Okay, so we are ending our today's session over here. If you have any query, then contact me or write in a comment box. I will try to solve your query as soon as possible.